Okay, that was forward selection feature ranking. So next is backward elimination and random subspace selection. What is that? Well, the general approach is now the other way around. We start with the complete feature space. So before we started with the empty space, so to say, and just added the k best features. Now we start with the complete feature space and delete the worst features, the most redundant features, or the most irrelevant features. In that case, the most redundant features actually. And backward or greedy backward elimination is you just generate all subspaces of the feature space initially, f. So f is n-dimensional, and you generate all n-1 dimensional feature spaces, subspaces of f. Then you evaluate all those with a quality measure, and let r star be the best one with respect to this quality measure. Then if you already have your target dimensionality, you keep it. Otherwise, you start again over with step 1 on r star, of course. No? So r star now is d-dimensional, and then you again generate all d-1 dimensional subspaces, again evaluate, and you do that with the best one always in step 2, as long as you have not reached your target dimensionality. Quite simple, actually. Okay. That is useful actually in supervised and unsupervised settings now, because you can also now in the lattice scenario measure structural characteristics. Well, you can do that also in the feature selection, in the forward feature selection, but here it's really worth it, because you always evaluate feature subsets and not individual features. So measuring structural characteristics in individual features is usually not a very good idea, because it's just something. But in that, especially in the unsupervised setting. So, but now in the backward elimination, since you start off with the entire feature space, you can really probably measure some structural characteristics. So it's also useful in the unsupervised setting. But we still try to be in the supervised setting here. The whole thing is typically a greedy search, because we typically assume that there is no monotonicity on the quality measure. So if we would have some monotonicity, we could of course apply branch and bound like a priori or FP growth in the item set mining problem. Okay, so let's have a look at the quality measures here. So some proposed quality measures for this backward elimination is, for example, a distance-based approach. So the idea, again, in a supervised setting is we want to evaluate the quality of a subspace by the distances between the within class nearest neighbor and the between class nearest neighbor. So the within class nearest neighbor is obvious of a given object is obviously the nearest neighbor within the class. So only considering the class members, you can compute the nearest neighbor of an object only considering the class members of the same class. And the between class nearest neighbor of an object is obviously the nearest neighbor among all objects that are not the same in the same class as the object. And for each object you do that, you compute the distance to the closest object having the same class, which is denoted as this one here, and in a specific subset R, subspace R, of course, and the the closest object belonging to another class, which is denoted here. So you see the difference here: nearest neighbor within the class, nearest neighbor in all other classes here. So the Ci is the same class, and the Cj here is the different class. And then you just compute the difference here by just computing the fraction and normalize it here by the number of training samples. This quality measure is not monotonous. By deleting a dimension, the quality can increase or decrease. You can think about that. That's easy to see. So in that case, it's obviously not monotonous. So you can only employ greedy search heuristics here. So another thing is model-based. So in that case, you directly employ the data mining algorithm, so kind of wrapper method to evaluate, or a kind of embedded method. So you, for example, you train a naive Bayes classifier in in all those candidate subspaces here. Yeah, so those are the candidate subspaces are here, and you just train, for example, a naive Bayes or something else, some model here directly, and evaluate the whole thing. Yeah, yeah. Some practical aspects that only works if the success of the data mining algorithm can really be measured, which is typically the case. So, for example, you can use class accuracy or precision or recall or F measure or whatever, false positive, false negatives, whatever it is important in your application. Of course, the runtime for training and applying the classifier should be not so high, because otherwise it just burns. And the classifier parameterization should also be not of great importance, because otherwise you need a very costly hyperparameter tuning, which pays into this point here, that the runtime may be quite high, and then the whole runtime is just a nightmare. Yeah, and the test set should have a moderate number of instances. Again, the same argument that the runtime just doesn't explode here. Yeah, short discussion. It considers complete subspaces. This is definitely on the pro side. Yeah, so multiple dependencies can be explored actually, and it can recognize and eliminate redundant features, which is also a good point here. Downside, the test with respect to the subspace quality usually requires much more effort. Yeah, so if you train something here, it's much more effort. So the whole thing requires probably much more time. And all solutions, of course, employ heuristic greedy search, because we do not have monotonicity on those quality measures. So in that case, again, we may not find the optimal feature space with respect to the quality measure. But okay, we know it's approximate.